Hello, everyone. I am Dr. Anup Narayanan, Associate Professor in the Department of Pharmaceutics at NGSM Institute of Pharmaceutical Sciences. In this lecture, we will be discussing two important distillation techniques: steam distillation and molecular distillation. Both of these methods are particularly important when dealing with heat sensitive substances which are commonly encountered in the pharmaceutical and natural product processing. We will explore their principles, equipment design, working methodology, applications in pharmaceutical sciences. Let us begin with steam distillation. Steam distillation is a specialized distillation technique carried out using steam. It is primarily used for substances that have high boiling points, tend to decompose at their normal boiling temperatures, are miscible with water, and are in conventional distillation. Such compounds cannot be safely distilled because high temperatures may lead to degradation. Steam distillation solves this problem by enabling distillation at temperatures significantly lower than the normal boiling point of the substance. This makes it especially useful for extraction of volatile oils, purification of heat sensitive compounds, removal of non volatile impurities, and it is considered a type of differential distillation and it provides an effective alternative to vacuum distillation in many cases. The principle of steam distillation is based on the behavior of immiscible liquids. When two immiscible liquids, such as water and an organic compound, are heated together, they exert independent vapor pressure. The mixture begins to boil when the sum of their vapor pressures equal to atmospheric pressure. This means the mixture can boil at a temperature lower than the boiling point of either component. Let us take an example. Turpentine has a boiling point around 160 degrees Celsius. However, when it is mixed with water, the mixture boils at approximately 95.6 degrees Celsius. This reduction in boiling temperature occurs because water contributes its vapor pressure, the organic compound contributes its vapor pressure. Together, they reach atmospheric pressure at a lower temperature. This principle allows us to distill high boiling, high sensitive, heat sensitive substances safely. Let us now examine the laboratory scale apparatus used for steam distillation in detail so that you can clearly visualize how the process operates step by step. The setup consists of four essential components, each with a specific role in ensuring efficient distillation. First, the steam generator or a steam can. This is typically a metallic vessel fitted with a safety valve or a safety tube to prevent the pressure buildup, a delivery tube through which steam is directly going into the system, and the function of this unit is to generate a continuous supply of saturated steam which act as the distillation medium. Next, we have the distillation flask, which contains the material to be processed. This include a crushed plant material such as clove or eucalyptus leaves, or a crude liquid mixture containing volatile components. The key point here is that the material inside the flask is not directly heated to its boiling point. Instead, steam is passed through it. Now, as the steam enters the flask, it penetrates the material, transfers heat, and facilitates the vaporization of volatile components. Importantly, the volatile components vaporize along with steam, even though their individual boiling points may be quite high. The resulting vapor mixture then moves into the condenser. This is usually a water cooled condenser where cold water circulates externally. The hot vapor loses heat and condenses back into the liquid form. Finally, the condensed liquid is collected in the receiver. At this stage, because of the components are immiscible, the aqueous phase and the organic phase often form separate layers. This makes separation easier. So, overall, the laboratory setup demonstrates simple but powerful principle, and we are using steam as a carrier for volatile components, enabling distillation at reduced temperatures. Now, let us extend this understanding to the industrial scale steam distillation system, which is designed for large scale and continuous operation. In industrial practice, the basic principle remains the same, but the equipment is modified to improve efficiency, throughput, process control, and central component is the jacketed still. This is a large vessel equipped with an external jacket through which heating media such as steam or hot water is circulated. The purpose of the jacket is to maintain a uniform temperature to prevent the heat loss, to ensure consistent vaporization conditions throughout the process. Inside the still, we often have a perforated plate or a false bottom. This plays a very important role. It supports the plant material or feed. It allows the steam to pass uniformly through the material. It prevents direct contact of the material with the bottom surface, avoiding localization or overheating. When the steam enters from below, it races evenly through the perforations, ensure efficient contact with the material, maximizes the extraction of volatile components. Now, after vaporization, the vapor mixture is condensed just like in the lab setup. However, instead of a simple receiver, we use a specialized device called as Florentine receiver. This is designed specifically to handle immiscible liquid systems such as oil and water. Its function is to automatically separate the condensed liquid into two layers, allow continuous removal of essential oil, enabling recycling of discharged water, and the separation is based on the density differences. If the oil is lighter than water, it floats. If heavier, it settles at the bottom. This automated separation is crucial in industrial setting because it reduces manual intervention, improves efficiency, allows continuous operations, and overall, this industrial setup enhances the basic steam distillation process by ensuring uniform distillation, improving heat transfer, enabling continuous large scale production. And this is why the steam distillation is extensively used in industries such as pharmaceutical manufacturing, essential oil extraction, and perfume and flavor industries. Steam distillation has several important pharmaceutical applications. It is widely used for extraction of volatile oils such as clove oil, eucalyptus oil, and anise oil, purification of essential oils such as almond oil, distillation of components like camphor, preparation of aromatic waters. The major advantages include lower operating temperature, preventing decomposition, preservation of aroma and therapeutic properties, suitability for compounds with high molecular weight and low volatility, and this makes the steam distillation a high valuable process in both pharmaceutical and cosmetic industries. Now, let us move to a more advanced and highly specialized technique known as molecular distillation. Unlike steam distillation, which utilize the concept of immiscibility and vapor pressure addition, molecular distillation is fundamentally based on molecular transport under high vacuum conditions. This technique is particularly important when dealing with compounds that are thermally unstable, meaning they degrade even at moderately elevated temperatures. High molecular weight substances such as vitamins, lipids, and polymers. Highly viscous materials where the conventional boiling becomes inefficient. In conventional distillation, the separation depends on the repeated vaporization and condensation cycles. However, in molecular distillation, the process is designed to avoid bulk boiling altogether. Instead, molecules escape directly from the liquid surface into the vapor phase and travel towards a condenser. Because of this unique mechanism, the molecular distillation is sometimes referred to as short path distillation or non equilibrium distillation, since it does not rely on establishing full vapor liquid equilibrium in the traditional sense. This makes it extremely valuable in pharmaceutical applications where maintaining chemical integrity and biological activity is critical. To understand the molecular distillation in depth, we must first understand the concept of mean free path. The mean free path is defined as the average distance a molecule travels in the vapor phase before colliding with another molecule. Under normal atmospheric conditions, the molecules are densely packed. Collisions are very frequent. The mean free path is extremely short. As a result, vapor molecules cannot travel far without interacting with other molecules, which leads to energy loss, random motion, reduced efficiency in direct transport. However, when we apply high vacuum, the situation changes dramatically. At very low pressure, the number of molecules in the system decreases. Intermolecular collisions becomes rare and the mean free path increases significantly. In molecular distillation, the system is designed such that the distance between the vapor evaporating surface and the condenser is equal to or less than the mean free path. This is critical design requirement. Why? Because under this condition, the molecules evaporate from the liquid surface, travel directly in a straight path, reach the condenser without any collisions. This phenomenon is also called as free molecular flow. As a result, there is minimal energy loss. The separation is high efficient. Even very delicate molecules can be handled without degradation. This theoretical concept is the foundation of molecular distillation. Building upon the concept of mean free path, let us now understand the operational principle and design of the molecular distillation system. One of the most widely used configuration of the molecular distillation is wiped film molecular still. In this system, the feed liquid is introduced into a heated cylindrical surface. Now, instead of allowing the liquid to remain stagnant, the system uses rotating wipers, typically made with PTFE or other inert materials. These wipers perform several important functions. They spread the liquid into a very thin film, a uniform film. They continuously renew the liquid surface. They enhance the heat transfer and mass transfer. And why this is important? Because it increases the surface area available for evaporation. It reduces the distance of the molecules must travel to escape. It ensures uniform heating. And additionally, the liquid film moves downward due to the gravity and mechanical action with a typical velocity about 1.5 meters per second. This results in very short residence time and reduced exposure to heat and prevention of thermal degradation. This method is highly effective for heat sensitive drugs like vitamins, fatty acids, and bioactive compounds. Another advanced and highly efficient design is centrifugal molecular still. In this system, the feed is introduced into a rapidly rotating vessel, often described as a bucket shaped rotor. Due to high rotational speed, the centrifugal forces pushes the liquid outwards. A thin liquid film is formed along the inner walls. This thin film is then subjected to a radiant heating, which provides rapid energy transfer. Uniform temperature distribution, because of the film is extremely thin, evaporation occurs almost instantaneously. The vaporized molecules travel a very short distance and reach the condenser without any collision. The system offers several advantages: a very high throughput, often up to 1000 liters per hour, high precision in separation, efficient handling of viscous, high value materials, etc. And centrifugal molecular stills are commonly used in fine chemicals, pharmaceutical intermediates, and nutraceuticals and specialty products. To summarize, we have discussed two important distillation techniques: steam distillation, which is based on immersible liquids, vapor pressure addition, reduced boiling temperature, and molecular distillation, which is based on mean free path, high vacuum conditions, direct molecular transport, while steam distillation is widely used for essential oils, natural products. Molecular distillation is essentially used for high purity, thermally sensitive, and high molecular weight compounds. Both techniques highlight how modifying operating conditions such as pressure and phase behavior can significantly enhance separation efficiency. A clear understanding of these methods allow us to design a better pharmaceutical processes and ensure product quality and stability. Thank you for your attention.